then you have a map from objects to objects. Objects of C1 to objects of C2. You have for each x and y inside objects, you have a map. So this is phi. This is also phi. Morphisms from x to y are mapped to morphisms from psi of x to psi of y. This happens in such a way that all natural operations are preserved, like psi of x of phi of morphisms lambda times mu is psi of lambda times psi of mu, and psi of identity is identity. This is just functor, but then you want to have another functor phi, opposite, in such a way that psi times phi, this is an object, is isomorphic to phi, to psi of times phi of x is isomorphic to x. So this is an isomorphism. An isomorphism is a morphism which is invertible, meaning that you have and this isomorphism is functorial in such a way that it's compatible with morphisms. There was the formal definition last time. I'm not going to repeat it. So it should be formally, there should be a natural equivalence of functors between this and identity functor. Okay. So this was general notion of equivalence of categories. The specific, we need category of affine varieties. This was again last time, and category of affine generated rings. So you have C of T1 or Tn quotient by finitely generated ideal. In fact, all ideals are finitely generated. This will be next time. I mean, this particular ring. And then you have, this is one category, C1, for instance. Another category is category of affine varieties. Yes, and here we should also have non-nilpotence. So this ring should be reduced. This is one category. Another category of affine varieties, where objects are common zeros of sets of polynomials, and morphisms are polynomial maps. Okay, there is a natural functor from here to there, because the ideal is a set of polynomials, right? And the homomorphisms are polynomial by definition. And this is an equivalence of categories. This is what I will be proving today. Do you have any questions? Is it obvious to you already? Everybody? For whom everything is obvious already? Yes, please.
Definition of the algebraic subsets is only considered as a subset or it has some other structures?
Yes, it has its own structure, namely the algebra of functions, of polynomial functions on it. In fact, you don't need it embedded, because we already discussed that two algebraic varieties are isomorphic if you have invertible maps, polynomial maps from one to another. Like algebraic affine variety, x is isomorphic to y if there exist polynomial bijections from x to y, from y to x. And moreover, the polynomial functions, so you have say psi here, phi here. Then you can start with a function, take its pullback to y, take its pullback to x again, and then you take psi star, phi star of f is equal to f. So you have an invertible polynomial map, which are also induce isomorphisms on the rings of polynomial functions. This means that these are isomorphic.
But you are talking about polynomial injection.
Yeah.
On the Cn, that can only be the linear.
No, it's on the sets. There are subsets. Subsets. They consider as subsets in C and with ring structure on functions, on polynomial functions. This is our category. So the morphisms are polynomial maps, and then identity is a polynomial map. So if you have, polynomial map, you can have like x inside Cn and another y inside Cn. But they could be isomorphic by polynomial maps from here to there and from there to there. You don't need this polynomial map to be in the whole Cn. No, you need it to be isomorphism between, like bijection between these subsets. If the subset is a point, for instance, or empty set, this is a very simple condition. So all points are equivalent by trivial maps, like, for instance. More questions? I would really appreciate you asking questions, so don't feel. OK. This statement, the equivalence categories, is essentially strong Nullstellensatz, the strong theorem, Hilbert theorem about zeros. Nullstellen is zeros and zero set, and Satz is a theorem. OK. So let me introduce a couple of notations, definition. So if you have ideal I inside polynomials, I denote an V of I, zero set, common zeros. So this is a subset inside Cn. And then if you have subset Z inside Cn, we denote annihilator of Z is a set of all functions vanishing in Z. Let me give you an example. So example, of course, polynomial functions. Polynomial. When I say function, I always mean what is called regular function, which means restriction of polynomial. Example. So you have, let's Z be just the set of all integers inside C. Can you tell me what is an of Z? Anyone? Sorry? No, we need annihilator is a set of all functions. So it's an ideal. It's an ideal in polynomial ring. So what is the because you want your all functions vanishing in all of the Z, in all the set, in all these sets, so it's in only integers. 0, right. Because if you have a polynomial which has infinitely many zeros, it is 0. So you see, there is, generally speaking, you cannot recover z from annihilator. However, the theorem Nullstellensatz tells us that if you have ideal I inside T1 over Tn, and let's denote this R. R by I has no nilpotence. Well, from usual Nullstellensatz, the weak Nullstellensatz, we know that V of I is non-empty. But then it turns out that you can just recover the ideal back. You can recover the ideal back from its 0 set. There is one-to-one correspondence, just like it is predicted by this equivalence. The 0 sets gives you the ideal back. Not like here, because here we take 0 set. Well, we take annihilator. It's already you can recover this set from the ideal, but you can do that from algebraic sets. So if you have started from algebraic set, so the corollary, if Z is algebraic, this means that Z is the common zeros of some ideal, right? This is definition. And then we can also remove all nilpotence by adding the, well, you can easily see. Then annihilator of V of Z is V is I, again, by this theorem. And then you can do it again and say that V, well, you can repeat it. There is one-to-one correspondence. So if we can again, you can recover Z from I, and you can recover I from Z. That's all. Questions? So I'm now going to prove this theorem unless you have some extra questions. No questions? Is the statement clear? Okay. Yeah, before I do that, let me deduce this theorem about equivalence of categories. So it was a theorem from the Nullstellensatz. There is essentially nothing to deduce. It's essentially a tautology. Except that you have the definition of equivalence of categories is tricky because, the category which has countably many objects, which are isomorphic, is equivalent to category which has just one object, which is isomorphic to itself. So equivalence of categories is non-trivial notion. Okay, let's deduce equivalence of categories from strong Nullstellensatz. We need a functor. Yeah, of course, this, there are fine varieties and rings. It's actually contravariant equivalence. So equivalence, if you have a map from a fine variety to another variety, the rings go opposite direction. It was explained last time. Okay, so let's construct a functor. So proof of equivalence. I start with a functor from rings to affine varieties. So you have ring, which is by definition polynomials R by J. Okay, this J, it has common zeros, so it goes to V of J. Good. Opposite direction is given by you have Z inside Cn, and you map it to annihilator. So these are two functors which should define equivalence of categories. And they do, because annihilator of V of I is I, and V of annihilator of Z is Z. These both statements just follow from, you iterate this equivalence a couple of times and you obtain this. So this is directly, and this here you just replace Z by, because Z by definition is common zeros, you just replace Z by V of I. And you obtain that this is the same as V of I by application of this. So this is the same as I. Okay. So as you can see that strong Nullstellensatz is the same as equivalence of categories. I mean, this is a tautology. You just have two functors. They are one is inverse to another, and of course, yeah, that's all. So in the end, you obtain, you started with a ring, you obtain the same equivalent, I mean, isomorphic ring in the end. Okay. Do you have any questions to what was there? Now the localizations. Who knows about localizations already? Please raise your hand. Well, it's a very basic and very important notion of commutative algebra. For instance, the easiest way, well, there are many just elementary results which can be proven with localization, and it is important. So we shall use it all the time. It's one of the most basic tools in commutative algebra. You can do it even in non-commutative situation as well. It doesn't. But the idea, you should remember how you construct the rationals, the set of rationals from integers. So suppose you have F or S subset in ring R subset, which is closed under multiplication. I think in here I use only localization. I mean, S is just, for instance, S is F squared, F third, and so on. This is an example of S. Then you can consider a new ring, which is denoted definition, localization of R in S. You can write R of S minus 1. So it's a ring formally generated by fractions. Ring generated by fractions. R divided by S, where R belongs to our ring and S belongs to this subset which we use for localization. For rationals, it's just all non-zero integers. So it's and you have relations. First, A by B plus C by D is equal to AD plus BC divided by BD. Standard relations for adding fractions. And second, if you have A divided by S1 is equal to A divided by S1. You can cancel S upstairs. Do you have this notion, rings generated by generators and relations? So the idea is that you just have all formal, you add monomials by the generators and you take a quotient by the ideal generated by your relations. In your case, you have two relations, well, main relations, but two types of relations, adding fractions and cancel the common multiplier. You have done that a lot when you studied rationals. This is how people construct rational numbers. Okay, but for when you have this localization just by one element, it's even easier. Sorry, Mark. So if you have R of F minus 1, where F is an element in this ring, you can take the ring of polynomials and take its quotient by T, F is equal 1. All right, this is precisely, you just added one more generator such that Tf is equal 1. This means that you just added F minus 1. So it's R of F minus 1. It's a fractions with denominator which is F. So in particular, it's finally generated ring. Okay, there are a couple of examples. There's ring of rational numbers with denominator 2 or power of 2. You just obtain it from integers by taking f equal 2. And there's another which is called the ring of Laurent polynomials. It's just polynomials from t and t minus 1. Again, you start with polynomials and you take f equal to t minus 1. Am I clear? Good. Okay, I already told you why it is finally generated, sorry. But there's an important claim which sort of explains in particular how one can use localizations. Namely, localizations are never zero unless you take a localization over something which is nilpotent. Okay, so claim. This is a really important claim. Let f inside R, and suppose, so this is a ring, that R of f minus 1, this is localization, is 0. This is 0 ring. Then f is nilpotent. Well, this is one if and only if, in fact. So the proof actually proves the equivalence. But the other direction is easier. Okay. I will, since we need it only in one direction, I will prove in one direction, and you will easily see how to prove an opposite direction. Okay, so proof. Step 1. We have a polynomial ring quotient by the only relation. And since 1 is equal 0, this means that if this ring R of f minus 1 is 0, then you have the only relation. 1 is equal to p times 1 minus tf, where p is a polynomial, p of t. This is a polynomial with coefficients in R. It just follows from the observation that I have erased that R of f minus 1 is R of t quotient by t f minus 1. So you take a quotient of this ring by the ideal generated by this polynomial. Okay. Now, let's look at this relation. So we can write the polynomial formally. P is equal to sum of ai t power I multiplied by 1 is equal to 1 minus tf times p means that ai is equal to ai minus 1 times f. I mean, this is just two polynomials, so it's a sum of ai t power ai t power n I minus ai minus 1 f t power I. So, and since the polynomial is 0, polynomial is equal to 1, then all coefficients with t power I with I positive should be 0. This should cancel with that. So this is true. But then, and also we should have a0 is equal 1, because this is the only contribution this polynomial can have to the 0 t power 0. Okay, but since the polynomial is finite, this means that a n for some very big n is equal to f power n is equal to 0. Because it can't be infinite. It has to be finite. Well, in other words, you can just remember that 1 over, 1 minus t f minus 1 is sum t power I f power I. If this is invertible, this should be finite. This is not a proof. This is a heuristic explanation why it should be true. Anyway, yeah. So this gives, then the f is clearly nilpotent. And converse is also true, because if f is nilpotent, this would be a finite polynomial, And you would have 1 minus tf times this polynomial p of t is equal 0, is equal 1. But this is 0 in our ring, so. Okay, did you have any questions? Was it clear? Anyone? So this was localization. This is what you do if you want to produce rational numbers from the integers. Now there is another really important notion, which is a notion of a spectrum. This is, the point is that, as we discussed already, the points on algebraic variety are the same as maximal ideals in the corresponding ring. The problem is that if you have morphisms, like homomorphism of rings, this doesn't bring you maximal ideals to maximal ideals. No. What you know that all prime ideals go to prime ideals, but maximal ideals are bad. They don't go to maximal ideals. By the way, do you have an example? Like morphism of rings such that maximal ideal doesn't go to a maximal ideal? So let me write this in as exercise. This is important. Find rings R1, R2, homomorphism phi from R1 to R2 such that phi minus 1 of a maximal ideal is not maximal. So the idea is that with primes it is true. If you have a prime ideal here, the quotient has no zero divisors. You take its preimage. The quotient also here also doesn't have any zero divisors because let me explain about preimages of ideals, and then we'll return to. So you have a map. You take phi minus 1 of an ideal, say I. Suppose I is a prime ideal. This means that you have R1 quotient by phi minus 1 of I goes to R2 quotient by I, right? This is just a quotient map. This has no zero divisors, and this is an embedding because you just take a quotient by all elements which vanish in R2. I mean, you take preimage of 0. So all elements which vanish in R2, after you take the quotient, become 0. So this is injective map. And if this has no zero divisors, this ring has no zero divisors. This is why preimage of a prime ideal is prime. Now let's about maximal. Can you give me, think about any morphism of rings. Yes, please. Yes, more specific. So which map you consider? C of x, y, z so this is your source ring, and what is your target ring? C of x, y, Z, and then you localize it over which set? Just you localize Z minus 1 and Y minus 1, or what? What do you localize? Or all elements which don't belong to some ideal? Or which set you localize?
The complement of the ring of the prime of the ideal prime generated by X and Y.
Okay, so you take all a row which doesn't belong to an ideal generated by X and Y. Good. So here you have a maximal ideal, namely, obviously, everything generated by X and Y is maximal ideal, and here it is not. In fact, it's a very complicated example. Let me give you a simple example. So you have Z goes to Q. In Q, you have just one ideal, namely 0. There's no other ideals in Q, right? I mean, it's a field. And the preimage of 0 is 0 here. So you have 0 ideal in Z. The quotient by the 0 ideal is Z. It's not a field. It's not a maximal. It's prime ideal, but not maximal ideal. And here it is maximal because there's just one ideal. But thank you very much. It was a good example. Okay. So it was actually a Grothendieck's idea that you should really, you don't need, I mean, I think Zariski, there's even a notion of Zariski spectrum. He thought that you should study the set of all maximal ideals. But then Grothendieck realized that it's bad because it's not functorial. You cannot, if you have a morphism of rings, you don't have a morphism of their spectra. But you have morphism of the set of prime ideals. So definition, spectrum of a ring R is the set of its prime ideals. Okay, so this was this exercise that the preimage of prime ideals is a prime ideal. I told you that, but you should be able to do it yourself. Yeah. In other words, here is somehow misplaced. But anyway, so let's state this result. This is what happens when you do localization. It turns out that localization just removes some prime ideals and leaves the rest. This is important property of localization. So proposition. So here I do localization with just one f, but it doesn't matter. Yeah. It's a strange statement, something wrong with it. But anyway, R f minus 1 to R gives injective map of spectra. You should think of really spectrum is just the algebraic variety. This is what is really algebraic variety, just spectrum. Okay, so let's prove that. So you have two P and Q, two ideals in sorry, actually, the map is in this direction, of course. The spectrum is that direction, and the map of rings is this direction. So this is two ideals in the R of f minus 1. Here I use the brackets to denote the same thing. And then we expect, suppose that, oh, sorry, yeah. No, this is mapped to that, this is mapped to this. Yeah, and then we have to, P is equal to Q in R. This means that P intersected with R is Q intersected with R. Because this is, I mean, this, well, this is what we, at least intuitively, this is what we have. For instance, when we localize, we actually add more elements. Our ring gets bigger, but its structure gets simpler because we just localized, like mapped, went from integers to rationals. But so what does it mean that they're the same in R? This means that for each, so let's consider their preimage P1 inside, so this is preimage. So let's denote this by phi, phi minus 1 of pi, Q1 phi minus 1 of Q. And then their equal means that for each, well, you can actually recover P from P1 as follows. You take well, for each P inside P1 and each Q inside Q1, since they're equal in, so this by assumption they're equal. Yes, Q well, I'm tired of that. Let's leave it as an exercise. We're not going to use it anyway. And this is obviously wrong as it's written. So I leave it as an exercise. It's obvious. Okay, now near radical. A near radical is just this ideal generated by all nilpotent elements. Is ideal generated by all nilpotent elements in R. And the result, we discussed that, and you even told me that you know this. So theorem, nil radical is intersection of all prime ideals. And the proof is simple. Well, first, of course, if you have an nilpotent element, it cannot be outside of a prime ideal. What is a prime ideal? It's an ideal such that you multiply any elements outside of this ideal, you obtain something which is outside of this ideal. You can't have nilpotents because the power of nilpotent is 0. So nilpotents belong to all prime ideals. Am I clear? Conversely, suppose you have something which belongs to intersection of all prime ideals. So X belongs to intersection of all prime ideals. Now we take localization with respect to X. So R of X. And, well, if it is, this could be a zero ring. But this would mean that x is nilpotent, we are done. So if x is non-nilpotent, this means that this is non-zero ring. But then it has a maximal ideal by its own lemma. So then R of x minus 1 has maximal ideal. Okay, then you take maximal ideal P, then R intersected with P. Well, you take just preimage under this map. Is a prime ideal. Is prime ideal. Now, this ideal can't contain x, because if it contains x, then it contains unit in this localization. And this is impossible. So this is not containing x. That's all. So this result about localization in particular brings you such a theory. Okay. Now this is something which van der Waarden calls Rabinovich trick, after a scientist. I don't know anybody anything about this scientist, but it's simple, and this is what is used to prove that the Nullstellensatz. It's proved with localization. So the basic argument is based on localization. So let's start with the trick. Theorem 1. You have an ideal. No, this it can be any ideal. Inside a polynomial ring. And you have a function which vanishes on its zero set. F restricted to zero set of I is equal to 0. Then certain power, then there exists n such that certain power of n belongs to this ideal. You see, this is almost Nullstellensatz, because Nullstellensatz tells us that, but it wants the quotient by this ideal to be nilpotent, and it tells us that if you have something which vanishes in zero set, it belongs to this ideal. Well, we're almost there, so it's even stronger result, in fact. So proof, step 1. Okay, so let's add one more variable. So you take one more another ideal, I1. This is an ideal in a ring, which is like, here you have t from 1 to n. Here we'll have c of t1 dot tn plus 1. And this ideal generated by I, and now we localize by f. So f tn plus 1 is equal to 1. Well, minus 1. The good thing about this ideal is that it has no common zeros. Because any has I1, then I1 has no common zeros. Why? Well, first, it contains all elements from I. So because if z1 dot zn plus 1 belongs to zero set of the ideal I1, then z1 dot zn belongs to the zero set of I, right? Because, I mean, the functions from I, they don't care about the last variable, and they vanish on the common zeros of the first. So it's like cylinder. Just multiply the zero set by adding extra variable. But then f restricted to this set is non-zero to v of I. So this is better to, to v of I times c is non-zero. Nowhere. Oh, sorry, is zero everywhere. Is zero, but then this function is non-zero. This means that f tn plus 1 minus 1 restricted to this v of I times c is non-zero. It's nowhere zero. So everywhere. Because 1 is non-zero and f restricted to this set is 0. We obtained an ideal which has no common zeros. Again, because common zeros of this, first there is this set, but then the extra generator which we added just is non-zero everywhere on this set. Okay, but then you have the Nullstellensatz, which says that, okay, you have an ideal which has no common zeros. It's not an ideal. In fact, it contains unit. So this means that I1 contains unit. Okay, now let's return to the localization. You have, let's consider the quotient. So this was step 1, this is step 2. You have R by I. This is our quotient ring, and it has, consider its map to well, what we can do like consider f, localize it by f. And of course, this is the same as we just discussed. It's the same as this ring, as R of t n plus 1 quotient. Well, here and everywhere R is this polynomial. So this is the same as quotient by I1. I mean, this is by definition. What we did, we just localized. We added one more variable and this relation. This is the same as doing localization. So this is the same as, but this is zero ring because this ideal contains a unit. So this is 0. And this means that f minus 1, well, f is an nilpotent in R by I. This means that f power n belongs to I, and this is something we just needed to show. Okay, so the proof is done. You see, just reduce everything to weak Nullstellensatz. Very simple by doing localization. You take a function okay, this function is bad, it doesn't vanish in our zero set. Let's localize this function and prove that you will have, well, this would give you an ideal which has no common zeros. It is it contains unit, and we're done. Okay, then the strong Nullstellensatz is just a special case of this result. So corollary. So this statement was, there are no assumptions on I here. Now let's do assumptions. So suppose that quotient, like polynomials t1 to tn over I, has no nilpotence. Then annihilator of v of I is equal I. Okay, this is because if you have something which vanishes on v of I, because, proof, if f is 0 on v of I, this means that f power n belongs to I. But since the quotient has no nilpotence, and this would mean that this is nilpotent in a quotient, then f belongs to I. So we proved that annihilator of zero set is the same ideal. Do you have any questions, comments? Okay. Do you want me to give you a break, like 5 minutes? Of course, I was late, but what I want is I want to print the new assignment. So you have 5 minutes break until 48 minutes, and then we'll have 10 more minutes to work. And I will print now the assignments for the next monitoring session. We have an equivalence between algebraic objects, rings, and geometric objects, algebraic sets. So how many of you know what is a smooth manifold? Please raise your hand if you know what is a smooth manifold. Okay, so the idea is that the most 9 out of 10 geometry studies manifolds. Manifolds are topological spaces which are locally homeomorphic to a round ball in Rn. This is manifolds, but typically people study smooth manifolds. I think next time, so how many of you know the proof of inverse function theorem? Like quick inverse function. Inverse. It's about half. Well, I will try to do it next time and very quick. So the idea is that there's this property of being manifold is called smoothness, and smoothness is actually an important property of geometric, like algebraic set, and you can study it from algebraic point of view. So yeah, so maybe I should start with definition of submanifold. So definition. Oh, do you know what is diffeomorphism? So who knows what is diffeomorphism? Diffeomorphism is a map which is invertible, and inverse has all derivatives. It's smooth. So smooth submanifold in R to n or Rn M inside Rn is a subset, like smooth M-dimensional, you have to fix dimension, is a subset such that for each point x inside M, there exists a neighborhood U containing this x. This is a neighborhood in Rm. And diffeomorphism. Diffeomorphism means that it is an invertible map which is smooth, and inverse is also smooth. It has all derivatives non-zero. Diffeomorphism from U to a ball, a B in Rn, such that, let's call it psi, that psi of M intersected with U is just a hyperplane, all M-dimensional plane intersected with a ball. So smooth manifold, submanifold is a submanifold which is locally diffeomorphic to just a coordinate plane. And of course, people study manifolds a lot for many different reasons. Mostly because they are like locally isomorphic to themselves. And this is not true if you consider singular varieties, which are singular is not smooth. So non-smooth guys, they're all different. There's lots of local moduli, they're even in locally they are all different. It's very hard to, and for manifolds you can actually have coordinates, because locally a manifold is isomorphic to a plane, and on a plane you have coordinates. So definition, if you have A inside Cn, algebraic set, and the point x inside A, it's called smooth. X is called smooth. If A is a smooth submanifold of Cn, which we now consider as R to N, in a neighborhood of X. So it's the same as here, just in the neighborhood of X. And of course, A is smooth. If all points X inside A is smooth, and X is singular if it's not smooth. So this is sort of topological property of algebraic set. But it turns out that you can, in fact, do it very easily by algebra. Yeah, the first observation is that you can actually, your diffeomorphisms to a ball can be chosen polynomial. So since we didn't start with inverse function theory, I will postpone the proof until we do it. But if you know, you can just read the proof. So proposition. You have X inside A, smooth point. Then there exists coordinate system. Namely coordinate functions as in this, in a neighborhood of x which are polynomial. So this is already something. This means that we can somehow at least try to characterize smoothness polynomial way. Now, this is real magic, and I will return to it next time because it's complicated magic. And here we shall stop now. So, theorem. First, if you have a maximal ideal, Mx, maximal ideal of a smooth point, x inside A is m-dimensional, there's actually some confusion because here we consider it as a real, here we consider it as a complex. So the problem with dimension. So this submanifold m-dimensional should be 2m because it's complex dimension 2m. M-dimensional, then maximal ideal, quotient by square of maximal ideal, is also m-dimensional. And this is, in fact, an equivalence. So this is how one characterizes the smooth points. We shall return to smooth points later in the course a lot, but let's do what we can next lecture, and then we shall go. Have you done the regular local rings from commutative algebra? Well, there is a commutative algebraic characterization of smoothness, which is called regularity. We shall return to it, but not now. Okay, so we're done, and we shall meet next Monday, I suppose. Yeah?